Okay, first of all, I'm recording up a lecture. This is going on YouTube, so nobody say anything crazy. And that's my job. Now, I still expect attendance, but if you really have a legitimate reason for missing a lecture, I generally have these lectures posted on YouTube sometime the same day. Or you might want to go back anyway in case you missed something when you were here. So on the syllabus, there's a course website, which I also sent a link to an email that all of you should have gotten. You definitely want to go there often. The lecture notes, I have a full set of lecture notes, 100 pages worth or so. That's already there, and I'll be following very closely, more so than a textbook. In fact, I don't even have a textbook right now. Not yet, anyway. But I will be assigning homework problems on that, more on that in a second. There are your grade comes from homework assignments. There will be 2 tests during the semester and a final exam. I do put practice tests on the website. In fact, they're already there from the last time I taught the course. There might be slight changes, but you can get an idea of what you're going to have. The textbook, Elementary Differential Equations and Boundary Value Problems, is now the 10th edition. Like most math books, they change editions often. So I do have a textbook. It's the old edition. I'm still waiting for the new one. Okay, you have your grade breakdown below. So a small portion of your grade is attendance. I do expect people to show up to be engaged, to at least take 50 minutes to stay off social media and try to pay attention and try to ask questions. If you we're past, the thing that's important to keep in mind is in Math 285, we're past a point where you can always expect to just sit there during 50 minutes and come out of there following it all. There's going to be things that will slip through, and that's where you need to either take some steps, either contact me after class, see me in my office, or shoot me an email, look through my notes. It's a good idea to look through the notes before class too, to get an idea of what I'll be talking about, because like I said, I will follow this as closely as possible. Basically, unless there's a hurricane, this is what's going to happen on each day. And yes, I have had to make that disclaimer. The homework, there's be 2 types of problems I'll give. There's reading questions, and then there's exercises from textbook. Reading questions I make up myself that are more about the general concepts, not just a solve this equation kind of deal. One thing I want to point out is I know that you can find solutions to homework problems online, sites like Chegg and so forth. If you're just going to go copy a solution, I consider that academic dishonesty. Don't do it. I can now give you an XF grade. Does anyone know the difference between an XF and an F?
You can't replace an XF.
Cannot replace it. Homework, those questions count for 15% of your grade. It's a not negligible amount, but it's not worth the risk. It's something I've seen students do, and besides that, think about this for a moment. Is that going to help you at all for the test? So think ahead a little bit, and give yourself a chance to figure things out, or work with me. I'm here to help. This is the 4th university I've taught at, and compared to the other 3, USM students are, on an average sense, with some exceptions, the worst at seeking help. And I went to professors' office hours all the time. Now, I know Reagan was president back then. It was a different time, but still, it's something that made a difference to break down some misconceptions, get past some mental roadblocks. Okay. Now, well, if you haven't visited the website, be sure to do that. On the lectures page, where I have the schedule on the site, that's where I'll post the links to the videos. It takes a little time to get them uploaded and enhanced and all that, but I would say certainly by that evening, it'll be up since class is in the morning. Okay. Now, okay. All right, how's the syllabus? 6 minutes, not bad. I do want to see, because I don't think we have everybody here, and I know several of you already from last semester or other classes, but of course I want to know who everybody is. I know we have a pretty big polymer science crowd here, I understand? Okay, well, welcome. Okay, all good? See which of you people look like your sore pictures. Okay, Bass. Okay. I see you moved to the other side of the room from last time. Okay. You can't get mad at me if I mispronounce your name. I'm going to give it my best shot. Busal. Is that remotely right? Okay. Okay. Bordley. Okay. In some cases, the picture didn't come through at all, so I have nothing to compare to. Bossier? Bossier. See, I blew it. Okay. Bowman. Okay. Brumfield. Okay. All right. Ehlenberg?
Here.
Okay. Fairley. Okay. Gamire? Related to Balaram? You related to Balaram Gamire? Oh. Never mind. Okay. Graves. Okay. Corral.
Here.
Okay. Okay. Kolb. Okay. Leggett. Ah, okay. Yeah. Okay. Lott. Okay. Martin.
Here.
Okay. If I had you last semester, I'm still going to call you out because you're just a sea of faces right now. Nicholson. Okay. Norris. Okay. Okay. Yeah, right in front of me. Okay. Okay. Oh, you're here. Fine. Rester. Yeah. Okay. Richardson. Okay. Robinson. Okay. Okay. Rodriguez. Okay. Roland. Okay. Stevens. Okay. Stevens. Okay. Tahir. Okay. Thompson. Trigg. Wade. Carly Walker. Catherine Walker. Okay. Waltman. Oh, right. I knew he wasn't going to be here. Wow, everybody's here. Can we try keeping it up? More in a couple weeks? Okay. And last semester, 280 some were like, okay, you know, I post a video so you can just see those, but you know, 10 is still part of a grade, and I do that for a reason. Now, I will admit, when I was an undergrad, I wasn't always the best at attending class. In fact, I remember as an undergrad, a friend of mine, we both had to skip class, we're walking out of the building, and as I asked him, what's your reason for skipping today? I walked by the instructor. And I regret doing that. Not that particular incident, that was funny, but I regret that habit of just unplugging like that, always deciding at the moment I had something more important to do, because I missed out on a lot of things. Now, at least when I would not be in class, I did everything possible to stay tuned to what was going on. In fact, probably a lot more than people who were there. And that's something that's very important no matter what you do. If you have a legitimate reason, that's the thing you let me know about in advance, and then I can make a judgment call to make it slide. But otherwise, I'm just going to assume you're slacking. So don't. Okay. Quick word about me. So this is my 8th year at USM. I'm the director of a graduate program. My name is Dr. Lambers, or Jim Lambers. I got my PhD at Stanford in 2003 in scientific computing and computational mathematics after doing undergrad at a different black and gold school, Purdue. My specialty is what they call numerical analysis. That's a subject of Math 460 and 461. Feel free to join me next year if you can. Where problems like the ones we'll see in this class, differential equations, are also problems from calculus or linear algebra, are solved by computer instead of by hand. But here in this class, we're going to focus on analytical methods, and the two kind of methods certainly go together. I like teaching this class. It's only my second time doing this particular class here at USM, but it's one I like to do because this is where, as Dr. Schroeder says way too often, rubber hits the road, and you start seeing more applications, and more interesting applications than the kind you see just in an ordinary calculus class. I mean, in calculus you see things like, okay, area under a curve, the volume of this strange solid of revolution, and the occasional building a fence kind of problem. But the applications here are more interesting. Not all instructors spend time on that, but it's something I'm going to. Another thing is, I want to make this class more of an exploration of what you're accustomed to seeing. And that, what I mean by that is, I'm not just going to say, okay, here's the kind of problem, and here's how you solve it. I am going to show you how the methods can be built from the ground up as much as time permits. And it's something that I think is very important to understand, because mathematics isn't just following a recipe. You're really missing out if that's how you see it. Those of you who are math majors, especially licensure majors, who are going to teach it that way, that's not the viewpoint you should have. All of these techniques that we're going to see, whether it's in this class or other classes, were designed because there was a need to solve some problem more effectively, more accurately, more efficiently, and people put their nose to the grindstone and found out a way to make it happen. Possibly by taking a very scenic route, by making things harder at first to make things easier in the end. In fact, that's why you were using differentiation integration rules instead of you computing tedious difference quotients and Riemann sums, because someone took the time to make things more abstract, which seemed like a harder way to go to come up with a more effective solution. And it's that kind of, that's basically we're in discovery mode here. I'm going to show you where these things come from. So this is not a matter of you just memorize some things and regurgitate. You'll see my cautionary note about finding solutions online. That isn't learning. That isn't education at all. And besides, if I wanted to, but the expectation is that you use the higher mental capabilities of human beings, not behave like parrots. I'm not into memorize and regurgitate. If I wanted to lecture to a room full of parrots, I'd have actual parrots, because that'd be a lot more entertaining and colorful. All right, so that ends today's rant, and tune in for Friday's rant. Okay, now we have, I think, enough time to illustrate I'm going to go about things this semester. Okay, I apologize up front for my penmanship. It's actually better from the board than it is on paper. Also, when I ask questions, or if you're asking me questions, keep in mind I've been listening and enjoying thoroughly very loud music for longer than all of you have been alive. That means my hearing is not what it should be. So a lot of times if you guys are talking, all I hear is like, it drives me crazy. Also, we have 35 minutes left in this class, so I don't want you to start packing up under 32 minutes from now. That I will hear, and it annoys the bleep out of me. Okay, now, since this course is about differential equations, so in a nutshell, informally, bless you, is an equation involving derivatives of some unknown function, which is the solution. That's what you're going to be finding. So it's a reverse. Before, you're given a function, you take its derivative or you take its integral. Now you know something about the derivative of a function, or maybe its second derivatives, or use it in combination, and you're expected to backtrack to the original function. In fact, every time you computed an integral, you were in fact solving a very simple differential equation, not a very interesting one. On Friday, I'll talk about certain kinds of differential equations, the kind we'll focus on in this class, and certain other ones we won't get into, but are the subject of higher level courses that I would strongly recommend. But I'll get to some simple examples now. Okay. But I do want to mention certain applications, kind of equations that either we'll see in this class or ones I've covered in other classes or work with in research. Okay, a lot of physical phenomena can be described using differential equations, such as dissipation of heat energy. In fact, those of you who took 280 with me last semester saw me derive a partial differential equation that models this. So how temperature changes over time, accounting for heat sources, the initial temperature profile, things like that. Those kind of equations can be used to describe all kinds of phenomena that behave like in a like manner following diffusion. For instance, I use equations like this for image processing, removing noise from images or sharpening images. Wave propagation. Simple examples like a vibrating string, or the motion of a spring. That's what we're going to look at about halfway through the semester. Sound waves, water waves, earthquakes, how the shock waves propagate through buildings, things like that. Fluid flow. Very important for applications such as ranging from oil recovery, big deal down here in the Gulf Coast region, or animation. So in movies using CGI to simulate, for instance, one of the hardest scenes ever filmed was pouring a glass of milk in the first Shrek. Population growth, financial mathematics, all kinds of applications. Only a few of which we'll see in this class. So, okay. So I'm going to derive a simple example and then show how we can solve this kind of equation. Hopefully, do that in the next half hour. Now, I want to. Unfortunately, we have kind of a full room here, but because of recording, what I've done in the past, I actually use your space to put this computer. But I think we're okay for now. But I have to go to the other side of the room. So I think it's working okay, but we'll see. I'm hoping I won't have to eject you from that seat, but we'll see.
Fingers crossed.
What?
Fingers crossed.
Okay. Well, of course, I don't want anybody to drop, but okay. All right. But also, every now so often we're going to be going over here, so you might be in a rough spot.
Do I need
but,
to sit there and sit here?
Starting Friday, I'd recommend that.
Okay.
Yeah. Okay. But for today, we'll just make do. Okay. Whoops. I was writing in the non-visible part of the board. Okay. All right, I'm going to sort of fence myself in here. Okay. That's a very rough approximation. It'll look funny when you watch it, trust me. Well, once I was this is a director of a graduate program. We train the graduate teaching assistants before they go into the classroom. And one of them, when writing on the board, they would be writing like I'm doing here, and the writing keep going up and up and up and up and up. And we have to correct that. Okay. This first example is based on Newton's second law. What is Newton's second law?
Force equals rate of change of momentum.
Force equals what?
Rate of change of momentum.
Yeah. So mass times acceleration. Yeah. But yes, rate of change of mass times velocity. And we're assuming mass is constant in this case. Okay. So we can write this as m dv dt, where a refers to acceleration, v refers to velocity, m is mass, f refers to force. So this is going to give us one side of the differential equation we're about to derive. Okay, so apologies to anyone who's A, taken a physics class, and B, is really into it, because I'm just going to oversimplify things. Okay. So, falling object, we want to be able to describe the forces acting on a falling object. So in this simplified model, we're going to have force due to gravity, and we're going to use downward orientation. Which is why this term is positive. And then I'm going to add a term for air resistance, also known as drag. And V is the velocity again, like we have here. And gamma is the drag coefficient. Okay. So now we have two expressions for a force. So all we have to do is equate them. So we're going to have m dv dt is equal to mg minus gamma v. Okay. So now v, the velocity of this falling object, that is our unknown. So we need some way of solving this kind of differential equations. This is one of the first kind of differential equations that we'll cover, where you have a derivative related to some constant times the function itself, and then you have some additional term here, which in this case is a constant, but could possibly be a function of t, as we'll see later. Okay. If we were to solve this and get the velocity, what should we do to this to get the position? Anyone? How do we?
Integration.
Yeah, we integrate. So as long as we know the initial position, and then dv dt, that's the v itself is the derivative of position, then we can integrate v and get the position as a function of time that way. Okay, so this is one example. Now I'm going to show another example, which actually leads to what is mathematically the same kind of equation, but everything in it has a different meaning. Oh, this eraser is awful. I think this one's going to be the worst. Yep, it's worse. Well, until a few years ago, classes in this room were oriented that way. The instructor would be up there. And I found myself hating that board even more than whiteboards because running just wouldn't show up. And I think because they weren't so good about cleaning, it looks really clean now. Time heals all wounds, I guess. But so we just turned the room around. Okay. Okay. Yeah, I think we're good on this side of the room because at least I have, I have almost this whole board that I can use. Yeah, so no, I'm not going to kick you out. Okay. So a second example So R and D in this example are constants. So mathematically, it's a very similar form to the previous equation where you have the derivative of your unknown function p is equal to a constant times the same function p, and then you have some additional constant term. P refers to the population of some species. R is the rate of reproduction. Preferably positive. And D is the death rate of specimens. The number of specimens that die per unit of time. So naturally that term is going to be negative. So it's subtracting from population. And that could be due to whatever causes. Predation, natural causes, etc. I should point out one kind of equation that's related to this that I encountered when I teaching a calculus class. Here we have the derivative related to a constant times the function itself. But if I did something like this, like d p dt is equal to some constant times p raised to a power, even a power slightly greater than 1. Here we have the first power, but if we have power slightly greater than 1, this is the way I won't solve this now, but maybe some other time. But the way this equation behaves is the population at some finite time will go up to infinity, blow up to infinity. Whereas this one will just steadily grow over time if R is positive. So this is actually called the Doomsday Equation. You have population growth that is so excessive that at some point you just overrun with whatever it is. Apparently, it can be used to admittedly oversimplification, model the population growth of rabbits. Okay. Now, so a general form for both these equations is dy dt, or y is your unknown, is equal to some constant a times y minus some other constant b. So what I'm going to do now is step back from these examples and say, okay, how do we solve something like this in general? Now, I'm going to impose an initial condition. Y at some initial time t naught is equal to y naught. So all this put together is called an initial value problem. Because a differential equation by itself does not have a unique solution. If you impose appropriate initial conditions, then you get uniqueness. It's just like when you are evaluating integral. When you evaluate an indefinite integral, what do you always lose points for if you forget to include it at the end?
Plus C.
Plus C, because that is a simple differential equation that does not have a unique solution. If you have some initial condition, that would nail down the value of C. Okay, so initial value problems are what we're going to be studying all semester long. There are also other kinds of problems, like boundary value problems, and these come up in other courses. Okay, so how can I go about solving this? So first, I'm just going to rearrange it algebraically. Something that always seems to be risky proposition for math students at all levels, because no matter what the class, it seems the problem is always the algebra. And having taught 280 last semester, that was something that was still a problem. I saw things done to fractions that those fractions will never recover from. I saw many instances of confusing addition with multiplication. We kind of should be past that by now. And I'll point these things out as they come. But you have a hard time understanding material at this level if you don't have your act together at that lower level. Okay, so all I'm going to do is I'm going to Well, first, I'm going to factor out an a. So we get y minus b over a. And then I'm going to divide both sides by y minus b over a, assuming that y minus b over a is non-zero. In fact, we'll find that that's going to be true in general. So we have, I'm going to write this slightly differently because I want to emphasize that y is a function of t. So I'll write it as y of t minus b over a. And then dy dt, that's the same as y prime of t. And that is equal to a. All right. Now, the next thing I'm going to do is, since we have some equation involving the derivative, y prime of t, it makes sense that integration is going to be called for. But it's not something you necessarily want to do right away. For instance, if I just went ahead and integrated both sides with respect to t at the start, that wouldn't really help me. But choosing to integrate now is going to be helpful. Apologies to those who had to squeeze a really tiny dt in here. Okay. So, obviously the right side is going to be very easy to handle. But what about the left side? And you don't know what y of t is, but that's not the point. Just in terms of evaluating the integral, what is something that we can do to this integral, and something you've done many times before, that would make it a whole lot easier to handle? Think of integration techniques you've already used.
The U substitution possible.
Yeah, let's do a U substitution. What should we set U equal to? To what? Oh, the bottom?
Bottom of the denominator.
Yes, as a matter of fact. So U is equal to y of t minus b over a. And when you're carrying a substitution, once you've settled on your U, what is your du in this case?
Y prime of t.
Yeah, you just differentiate this. So you get y prime of t dt. And that's convenient because this is your du. So now on the left side, you're just integrating 1 over u du. Oh, I went outside my visible area. Okay, so apologies to anyone watching. So I'll give you a moment there. Well, I guess you can pause it and make sure to get all that. Of course, it's also in the notes. Okay. So now that we have this substitution, let's go ahead and actually carry out the integration. All right. All right, so we have integral of 1 over u du is equal to the integral of a dt. So what are we going to get now? Natural log of not u, but absolute value. Yeah. And then the right side? Yeah, and we needed constant of integration. You only need it on one side because it's an arbitrary constant. If you had arbitrary constants on both sides, you could move one of them to the other side and have another arbitrary constant. So if you have indefinite integrals on both sides, you need the plus c on one side and only one side. Okay, now let's undo our substitution. So u is y of t minus b over a. Okay, it's y of t that we want. How do we get it? What can we do to this?
Raise everything.
Sorry, what?
E to the power. Of
Yes. Yeah. Remember, hearing sucks. So y of t minus b over a, take the exponential both sides, it cancels out the natural log, and we get e to the a t plus c, which I'd like to break up into two exponentials. So e to the at, e to the c. Okay.
Do we have to do that extra step?
In general, no. Look, okay. When it comes to tests, and I assume this is what you're really asking about, right? I understand that there's time pressure. I don't expect every little thing. I also actually prefer you not to take the time to simplify answers. It actually makes it easier for me to grade if you don't. What I want to know is, do you understand the method? Have you written enough to show me that you do? So, no, I'm not going to nitpick about those things. I'm going to do this I require myself to do this so that everyone here can more easily understand what's going on and where each step comes from. It's not something I expect of you. Okay. Now, y of t is what we want. So we need to, if we were to drop the absolute value, all right, so if I go ahead and do that, then what happens to the right side because I'm dropping at absolute value?
Squares.
No.
Minus.
Plus or minus? Okay. Okay. So in effect, y of t might, so now I'll just rearrange and solve for y of t. Okay. Now, e to the c, regardless of what c is, that's going to be positive. But I have a plus or minus in here. So now I have b over a plus e to the at times some constant, which is allowed to be either positive or negative. So I'm going to condense my notation a little bit. I'll let d equal plus or minus e to the c. So now I have a solution in this form. Okay. So I have a solution. But I'm not done yet because I have to make sure that the original problem is that both conditions are satisfied. It's a good idea to, if you can, to verify that the solution really is a solution of the differential equation. Also, if there is an initial condition, some problems will have one, some won't, that that is satisfied. And that helps account for any arbitrary constants that you have, which is what this d is. So, does this actually solve the initial value problem? And does whoever watching see what I'm writing? No. Okay, now they can. So what I'm going to do is I could actually plug this into the differential equation. So y prime, I'll just differentiate this. That'll be easy enough. So we're going to get d times the derivative of e to the at, which is what? Yeah. So e to the at times a by the chain rule. So now, if we go back to the differential equation, so that's y prime as opposed to a times y. Okay, so now we have, well, I'll just write out the right side, ay minus b. So that's going to be a times b over a plus d e to the at minus b. So what will happen is, after I expand this, I'm going to get a's cancel. We get b plus ad e to the at minus b. The b's will cancel. So now we have, comparing this against this.
What does that say? Does that say A, Y to the?
ay of t minus b. You have a question? So, they match. Therefore, this is a solution of the ordinary differential equation, but we're still a matter of the initial condition. So, okay. That's going to give us an actual value for d. So what we do is we go ahead and plug in the initial time. Y of t naught is equal to a plus d e to the a t naught. And then we require that to equal some given initial value y naught. So now we can go ahead and use this to solve for d. So, so y naught would be, well, I can rearrange this. So d is equal to y naught minus b over a divided by e to the a t naught. All right, just rearranging things algebraically. But I'm actually going to write this a little differently. Well, how can I write this so that I don't have this down here? I want the exponential upstairs. What should I do? Sorry?
Change your exponent to a negative.
Yes. So we have y naught minus b over a, e to the minus a t naught. So now I have a value for d, and I can put that back into my solution. So the solution of my IVP, initial value problem, so that's an abbreviation that's often used, is y of t is equal to b over a plus y naught minus b over a, and then I have e to the a t at start, and then I can have this exponential too. I can combine those into one exponential. So e to the at, e to the minus a t naught, but I'll just, if I put these together, what's the right way to do that? Into one exponential. What do you do to the exponents? You add them. Some people multiply them. That's going to stop, right? Okay. Yes, by your laws of exponents, get e to the a, t minus t naught. Okay. Okay, so now we have a solution formula for any differential equation, initial condition of that form. Okay, that form for those of you watching. Okay. So notice we have this, how much time has passed since the initial time, t naught in this case. This kind of expression appears often in the solutions of these kind of problems. Okay. Now, what I'll try to do as often as possible is arrive at concrete solution formulas like this. It's not something that's always possible, but it's something that can be very convenient, especially on tests. Because then you're not having to go through the same laborious steps every single time and take up a lot of time. So any questions about how the solution was arrived at in the last 4 minutes that we have? Okay. Now, so what's interesting is to understand how the solution behaves. If I write this slightly differently, by taking that first term, the b minus a, and moving it to the other side, y minus by t minus b over a is equal to y naught minus b over a times e to the a t minus t naught. Now, let's assume the initial value of y naught is greater than b minus a. Then turns out y of t is also going to be greater it's also going to be greater than b over a. Why is that? Based on what I've written here, why can I say that?
Because you're subtracting BA from Y naught. Y naught's got to be greater for it to be a positive value.
Well, so what I'm saying is, if this is positive to begin with, this is also going to be positive. So, yet, what's left to focus on to explain why that would be?
So the factor, that's multiplying on the right hand side.
Yeah, it's exponential. Exponential is always positive. So since this is positive, this is going to be positive, therefore this is going to be positive too. So I could also say that if y naught is less than b minus a at the start, then y of t is going to be less than b over a forever for the same reason. Always a good idea to, once you have a solution, try to understand how it behaves over time. For instance, how does it behave as t goes to infinity? That's a very important thing to keep in mind. Especially if you're studying population growth. Is the population going to go to zero? Is a species going to die out? Or is it going to flourish? So these are the kind of questions that we ask about such solutions. Okay, so this is just a preview. We'll revisit these kind of equations in more generality shortly. Because we classify them in different ways. And I'll talk about more other kinds of equations, like linear versus nonlinear, ordinary versus partial, etc. On Friday. So, okay, get out. See you in a couple days.
Are there any